Section 3.6 is titled An Overview of Curve Sketching. Now, there are a lot of tools that you already know about graphing because you've had a lot of math. You know, or at least if we went through it again, you'd very quickly remember how to find x-intercepts, how to find y-intercepts. If we were dealing with a parabola, you'd know how to find maxes and mins from an algebra perspective. We've talked about finding maxes and mins from a calculus perspective as well. You know how to find asymptotes, all right? So where we're starting is with all that sort of background knowledge. I'll remind you of some of the pieces along the way. But we're going to incorporate some of these calculus concepts that we've been working with about maxes and mins and concavity as we work through that, okay? So not all of this is certainly brand new information. We're just adding to what you already know. So to start with some important graphical features, all of these are already written in your notes. You don't have to copy anything down if you've had this printed. But these are some guidelines as to how to make decisions about sketching a curve. You should determine what the domain and range is. So domain and range. Domain means all the x values. Are there any x values you're not allowed to have? In particular, those happen when we have denominators. You know, you can't let the denominator equal 0. They'll happen if you have radicals, you know, square roots. You can't have a value that's negative underneath the square root, those kinds of things. Range values are a little bit harder to determine. They kind of almost come for free as you keep working with the problem. But range values are your y values. If you were dealing with trigonometry, right, sines and cosines, it's going to be trapped between -1 and +1, you know, between for sine, the height and the heights, maximum and minimum heights for sine and cosine. If you are dealing with a parabola, you know that a parabola either opens up or it opens down. So sort of, if you will, half of the graph is untouched, right, because of the direction that it's opening. So there's some pieces with range that you can determine pretty quickly, and other pieces you get as you work your way along further. So the second thing is to determine intercepts, asymptotes, and symmetry. Okay, intercepts. Your x-intercept, right, is when y equals 0, and your y-intercept is when x is equal to 0. So you often do a little bit of algebra setting something equal to 0 and solving. Asymptotes. If there are asymptotes, they happen when the denominator is 0, right? Yeah. Symmetry. Symmetry is not something that we've talked about very much. Some graphs have it and some graphs don't. So some graphs have symmetry where it reflects over the y-axis. Think about a parabola. Sometimes it will do that. We don't have any functions that actually reflect over the x-axis and actually are also a function. So if you imagine like a sideways parabola that was right around the x-axis, that would have x-axis symmetry. That wouldn't be a function, though, because functions have to pass the vertical line test. So we don't have to worry so much about that. Some graphs are what we call, have origin symmetry, or they're what we call odd. And so with that, they look like a 180-degree rotation around the origin. So they do this rotational kind of feature. And if you remember a graph that looks like this would be an example of that. So we saw that recently. It was the graph of, I think it was the cube root of x. I think that was right. And then this is what it ended up looking like. So if you imagine spinning it like a dial, 180 degrees, it would land right back down on itself. That's a symmetry feature. And then the other pieces, part 3, are the calculus pieces that we're going to add in. So we're going to locate values for which the derivative, the second derivative, are either 0 or do not exist. And we're going to use those pieces of information to find maxes and mins, inflection points, concavity, increasing, decreasing. I could throw in there as well. So maxes, mins, increasing, decreasing, that all goes together with the first derivative, and then inflection points and concavity with the second derivative. These problems can get really messy, and it's really hard to ask you to do something on WebAssign that makes this actually feel like you're doing all the pieces in a way that it's genuine. So I've given you just a few examples to do inside of WebAssign to try to get your feet wet a little bit, but the bulk of what you're really going to do is more about the written homework, because you have to do it from the beginning yourself, going through all the pieces. WebAssign's best bet is to ask you very specific questions along the way. State the domain and range. Right? Find the x-intercepts, and it's very leading. It's a very leading kind of question. When in reality, those are just the pieces that you have to do in order to get the graph to look right. Should you check your graph on your calculator? Absolutely. I mean, because you've got it as a tool, right? We're not at the point where I'm saying you cannot use a calculator. There's some calculus classes that do not let you use calculators. I will tell you that. But this isn't one of them. All right, so you should definitely use what tools you have to check your work. So let's take a look then at a couple of examples of this. Our first one is actually a rational function. The directions all kind of say the same thing. They ask you to analyze and sketch the graph, label intercepts, max minimums, points of inflections, and asymptotes. So one of the things you might notice is that it doesn't actually tell you have to find the domain and range. And the reality is that the domain and range usually come about on their own as you're finding other pieces. For example, when you find the asymptotes, you're really finding the domain, or sort of the opposite of the domain, places where the domain doesn't have values, right? So those you kind of get for free. So we're going to take a look and we're going to follow their directions. They want us to sketch the graph, label asymptotes, intercepts, extrema, points of inflection, all that good stuff. And so as you're taking a look at the domain, which corresponds to asymptotes, what are the asymptotes, or what is an asymptote for this graph? All right, so remember asymptotes are lines, so can you be a little more specific for me, Jeff? Okay, x equals 0, very good. Is everybody good with that? X equals 0 is one of my asymptotes. Because the denominator equals 0 there, right? Yeah. So what that means is that my domain is everything else, so negative infinity to 0 and 0 to infinity. They go hand in hand. Now, that's actually the x, or not x, but vertical asymptotes, right? The ones that say x equals. There's also horizontal asymptotes. Horizontal asymptotes are determined when you look at the degree of the numerator, the degree of the denominator. I don't want to go too far down that bunny trail because you remember it. You probably just don't remember all the details. But when the degree of the numerator is smaller, this is a degree of 1, is smaller than the degree of the denominator, your asymptote is y equals 0 as well. Do you remember that? There's 3 cases. If the degree of the numerator is larger, there's no horizontal asymptotes. If the degree of the denominator is larger, which this one is, the horizontal asymptotes y equals 0. And then if the degrees are equal, you do the leading coefficients. So like if this had said x cubed and the denominator said x cubed, you'd look at the numbers in front, which both happen to be 1, and your horizontal asymptote would be y equals 1. So that's actually what's going on that. You can confirm that, and we will confirm it as we're working. We also then, that means have an asymptote at y equals 0. Now, that means, and you have to be careful, that it might be true that we never touch 0, because that's usually, like on the x-axis, that's usually what it means for a rational function, but it isn't always what it means. It means that we don't touch 0 on the ends of the graph. But we could actually cross it in the middle. So we'll come back to the idea of range in a moment and assess whether or not we actually cross the asymptote itself, and we'll decide, okay? So I'm just going to hold that blank for the moment, and we'll come back. Let's see. We need to do our x-intercepts and y-intercepts. So x-intercept, if you remember a moment ago, what I told you is when y equals to 0. And we have our y-intercept, and our y-intercept is when x equals to 0. Let's do the y-intercept first because it's the easiest. The y-intercept says plug in 0 for all the x's, and what happens if you try to do that? You get a 0 in the denominator, right? And we can't have 0 in the denominator, so there is none here, or no y-intercepts. We don't have any. The x-intercept means letting y equals 0. And in a rational function, that will only happen, right, for the whole function to equal 0 if the top is equal to 0. So for reality here, this infers that we're going to let the numerator equal 0. So if my numerator here, which is x minus 4, minus 4 equals 0, what x value does that happen at? 4. So I actually have an x-intercept at 4, 0. And I think that at this point we have at least enough information to start sketching a graph that has these features so that we can start filling in the details that are still there. So I'm going to switch to another screen to put these details onto a graph over here, and I've got grids. So we're going to have our x and y axis. We know that we have a asymptote at x equals 0 and an asymptote at y equals 0, which are the x and y axes. So I'm going to put them in as dotted lines to remind ourselves that towards the edges of these, I'm still getting close to them. And the last piece of information that we don't have labeled yet is that I have an x-intercept at 4, 0. So an x-intercept at 4, 0 would be roughly right. Let me use a different color yet. How about blue? 1, 2, 3, here. So right there is my x-intercept. Now, the fact is that I just put an x-intercept on the horizontal asymptote, didn't I? So this graph actually is going to cross my horizontal asymptote. So that actually means that that was the only place that I might not have had a y value, but I do have a y value there. So as I'm taking a look back over here at my range actually is negative infinity to infinity here. I don't actually have a place where it doesn't exist. Okay, everybody good so far? All of that is algebra. Okay, we haven't done any calculus yet. It's still maybe algebra you don't remember, and that's okay, but it's just algebra. So let's look at the calculus part of this next. The calculus part of this, which is the step 3 things here, have to do with finding the derivatives, the second derivatives, absolute or maxes and mins, inflection points, concavity, increasing, decreasing, all that good stuff. Okay? And all of that is associated with finding derivatives and setting up sign charts. So that's where we're headed next. So we're going to take a derivative of our function. So I have f prime of x, and we're ready to get going. So what is the derivative of our function? What rule am I going to need? Quotient rule. I am. And so my quotient rule says I do what first? The denominator and then the derivative of the numerator. So what's the derivative of the numerator? 1. And then I do the numerator, x minus 4, and the derivative of the denominator, which is 3x squared. And I write this over the denominator squared. And I have to clean this up, right? And I have to set it equal to 0 and find those potential critical points. Yes. Thank you. Get that in there. I appreciate it. All right. You ready? Cleaning it up? Bree says no. Are you okay?
Yeah. No,
okay. All right. So we have x cubed minus 2x cubed plus 412, 12x squared. Did we get all the pieces okay?
Yeah.
Why did I not write 2? I meant to write a 3, right? I was ahead. You're right. Okay, so we're distributing this through. At least that was our goal. So I have 3x cubed and 12x squared, and then I have a negative and a positive. And the denominator is x to the 6th. Awesome. Okay, my x cubes can combine. So I actually have negative 2x cubed plus 12 over x to the 6th. Are we all good? Yeah? Okay. So now what? Well, we set it equal to 0, or equal to does not exist. Now let me tell you, the does not exist here is sort of irrelevant. We know where this doesn't exist. Where does this derivative not exist? At x equals 0. But we know what happens at x equals 0 as well. What happens? There's an asymptote. So the does not exist part for this rational function doesn't give us any new information. But the sitting at equal to 0 part potentially will. It'll at least tell us some information about where it might be increasing or decreasing, where it maybe has some maxes and mins. So we're going to set this equal to 0, which really means setting the numerator equal to 0. Man, I'm really losing my values today. I guess it will. Thank you. My screen is much smaller than what you guys see on the whole board, and this is why I lose things, is because in order to write big enough, I have to make the screen large enough that I can write big, and then I don't see all the pieces. So that's what's happening every time I lose pieces, is I can't see it on my screen. All right, at any rate, there's some pieces on the left-hand side where they have things in common, right? There's some stuff in common on each of the terms. So what do each of these terms have in common that I can factor out? 2 and x squared. Good. So this gives me a negative x plus 6. Is that right?
Does it matter if we pull a negative out too?
No, it doesn't. You'll still get the same thing. So if you pull a negative out, you'll end up with x minus 6 in the middle. So you'll get the same x-intercepts, or the same the same solution, we'll say, to this part of it. And if I set each part equal to 0, here's 2x squared equals 0. And I have negative x plus 6 equals 0. And if I were to solve each of them, this is x equals to 0, and this is x equals 6. Yes? It's all good. I have just enough space if I shrink it a little bit to do a sign chart for this one. Okay, so we're going to set up a number line, and on our number line, we're going to have 0 and 6. And I know there's an asymptote at 0, that's fine. However, even though there's an asymptote at 0, doesn't mean that it couldn't change from, say, increasing to decreasing. Right? It could be decreasing before the asymptote and increasing after the asymptote or something like that. So I have 0, and I have 6, and I need to do test points in between them. So what's a test point you might want to choose before 0? -1. Between 0 and 6? And after 6? 7. Okay. And we're going to test them in the derivative right here before I ignored the denominator. I need all of that. So if I were to evaluate this at -1 into here, I need to know, do I get a positive or do I get a negative? That's my question. So let's see. You get a negative. I actually have written down, a positive. And Kaylee says a positive. Okay, so we get a positive. Let me change my color. How about the number 1? That one's a negative? I think it's still positive. Yeah? So if I plug in 1 on the numerator, I have a -2, I have a +12, which gives me positive, and the denominator positive. So this one's also positive. And then we want to plug in 7, and then we're not going to do that in our heads. Grab a calculator. Is that one finally negative? I think that one's negative. Okay. Positive, positive, negative. Sounds good to me. All right. First derivative. What does positive mean on a sign chart? Nope. Nope. It's increasing. There you go. You guys are thinking about second derivatives. Yep. So it's increasing. So this graph, we're just going to jot it down to the side here, is actually increasing from -infinity to 0 and 0 to 6. And it's decreasing from 0 to 6. I'm sorry, 6 to infinity. Here we go. That's what that says. Okay, well, we know what happens at 0. This is an asymptote. What happens at 6? Well, it's increasing and then it's decreasing. So what happens at 6? What's going on right here? It's a max. Not a whole, because I don't have any value that it can't equal, right? X equals 6 is a valid value, so there's not a whole. But I actually have a maximum value here. So those are the pieces of information I'm able to find with the first derivative. There is a max at 6 something. And how would I find the y value something that I don't know right now? Plug it into the original. So go back to the original function, x minus 4 over x cubed. And if you plug in 6, what will you get? It's big. I mean, it's small because the denominator is big. Yeah. Yeah, and if you want to use decimals, especially for the fact that we're going to actually be plotting them on a graph, it's 0.009. So it would end up being 2 over, I think it's 216 or something like that. Yeah, am I right? 216. It's not one I do very often. So you'd end up with, I don't know, 1 over 108. It's a big, it's a big denominator, so you end up with a very small fraction or a very small decimal. Okay. So what we know over here is that at x equals to 6, which is right here, I have a very, very small value, agreed? But it is positive, and it is a maximum. So I'll plot it, but it's not going to be plotted to scale because I can't plot it to scale. There's not a real good way to do that. But it's something like that, and it's a maximum. I also know that it is decreasing after that point of maximum, and it's got to be getting close to the x-axis. So you probably have a pretty good idea of what that would look like. Okay, the other pieces may be a little bit less clear, but let's actually figure out our concavity pieces to help us out too. Okay, so concavity is going to deal with the second derivative. So over here, this is kind of messy still. It's negative 2x cubed plus 12x squared over x to the sixth. But it could reduce, because there's an x in every term, right? Yeah, I mean, like we could make it smaller, and it might have been maybe helpful to make it smaller earlier. It doesn't really matter, but we could make that smaller. So for the purposes of what I'm doing now, are you guys good with me removing the part with the domain, asymptotes, all that good stuff? Am I good to delete that? Okay. And I won't move this completely. I'll just shift it and make it smaller so it's still there. All right, so we need to take this part that's blocked in blue, and we can actually divide each of the terms by x squared. So my derivative that I had before can be rewritten as negative 2x plus 12 over x to the fourth. Is that okay for everybody? And then we can take our second derivative from that. So second derivative. Second derivative, same as the first, right? Same as the first. So we do the derivative, or we do the denominator, and then the derivative of the numerator, which is negative 2, minus the numerator, negative 2x plus 12, times the derivative of the denominator, which is 4x cubed, over the denominator squared, which will be x to the fourth squared, which is x to the eighth. And then we're going to clean up that numerator, right? All this is, this, I mean, like we're doing the exact same process we just did because we're dealing with almost the same function, or at least a very similar style. So negative 2x to the fourth. We have positive 8x to the fourth, negative 48x cubed over x to the eighth. So negative 2x to the fourth and positive 8x to the fourth would be 6x to the fourth minus 48x cubed over x to the eighth. I didn't do it last time, so let's do it this time just to say that it won't actually affect anything. We can reduce all of these by a power of x cubed, right? So we can do that right now if you'd like. If you don't want to do that too, you can not, and you can continue, and it'll work out the same way. So this would be it would be 6x minus 48 over x to the fifth. Okay, are we good? Okay, cool. Now, if I set the numerator, 6x minus 48, equal to 0, and honestly, the denominator equal to 0 as well. We didn't have to do that last time because we still had a power out there to do that. This gives me x equals 0. That's fine. That's going to be on my sign chart. I know there's an asymptote there, but again, the concavity could change. What is this piece going to be? What's x?
8.
It's 8. Okay. So we're going to have a sign chart with 0 and 8 on there. Doesn't this just feel like we've already done it? Because we did 0 and 6, 0 and 8. And we test points around those. And last time we did negative 1 and 1, and so those were good. And we'll do just 10 or 9 or whatever you want bigger than 8. Okay, and we're putting them into the derivative. And it can be the reduced form of the derivative, so it can go into here if you'd like. So if you put in negative 1, what will you get? You'll get a positive. You get a negative on top and a negative on bottom, so it's positive. If you put in 1,
Also positive. Wait,
I think that one's negative.
yes, negative.
Okay, that one's negative. And then put in 10 or 9 or something like that. Is it positive?
Yeah.
Okay. So it's positive, then negative, then positive. So, again, we know what happens here at 0. This is an asymptote. What will be happening at 8 potentially is an inflection point, right? Because it changes from negative to positive. And in fact, it does. I mean, the concavity actually does change from negative to positive, so we will have an inflection point. So let's talk about the concavity real quick. So what's the concavity when I have the positives? Up, right? it's concave up, and when it's negative, it's concave down. So as we're writing out the details about concavity, just like I did about my increasing and my decreasing here, we have concave up from negative infinity to 0 and from 8 to infinity. And we have concave down from 0 to 8. I wrote infinity and I said 8. Let's try it again. 0 to 8. And we have an inflection point, like we just said, and our inflection point is at 8 something. How do I find out the something? Plug it in where, Reed?
The original?
The original, you got it. Yeah, we're going to plug it into the original function. So if I plug it back in up here, I'm going to get a big denominator again. I don't know what 8 cubed is, but the numerator will be 4. Kaylee, can you tell me what that would be as a decimal, since you've got your calculator going for me? 0.0008. Very small. All right, very, very small. Something smaller, tiny bit smaller than the number here over at 6. Tiny bit smaller. Okay, so let's do our graph real quick, because this one's almost finished up now. So it's supposed to be, on the 0 to infinity part, take a look here. I'm sorry, on the negative infinity to 0 part, it's supposed to be concave up and increasing. Those are the same intervals, 0 to infinity. I'm sorry, negative infinity to 0. So it's supposed to be concave up and increasing, and it's supposed to be trapped between asymptotes. So there's two options here. We either have to be up here or we have to be down here. That's what it means to be trapped between the two asymptotes, because we're on the left-hand side of the graph from negative infinity to 0. So the question is it on the top in quadrant 2 or is it on the bottom in quadrant 3? Right. You're right. It has to be on the top in quadrant 2 because it's got to be concave up and it's got to be increasing. And if I were on the bottom, it would be concave down and it would be decreasing, which is exactly the opposite of what we're looking for. So again, this is curve sketching. This is what it looks like. On the other piece, from 0 to 6, it's supposed to be, okay, increasing again, right? And here it's supposed to be increasing. And it's supposed to be concave down. It's supposed to be concave down even further than that. But certainly until 6, it's supposed to be concave down. So it's got to be increasing, and it's got to be concave down, which means increasing and concave down looks like this. And I do get to cross the axis. I already put the blue dot on there, right? I know it's going to cross there. And then the last piece is supposed to be decreasing. So from that point at 6, I'm got to be going downhill. And it's going downhill and concave down for a while, right? That's what this here says. I'm over here still. I'm still concave down for a while. And then once I get to 8, it's supposed to be concave back up. And it's really hard to draw this, but if you can imagine here, it looks something like this. If I were to sort of exaggerate it some just to kind of see what's happening, there are these points here, and on this point it's concave down, so it's looking like that. And then after that, it looks like this, right? Like if you zoomed in on your graph, this is the image that you would have. Difficult to draw, but nonetheless. Any questions about that? The other graph's easier. Rational functions have the most going on in all the details. All right, analyze and sketch. Same directions. You might be like, okay, well, this is a square root. Why is that easier? It's actually easier because there's fewer pieces of information. That's why. First of all, there's no asymptote, right? Nope, because there's no denominator. There are some issues with domain, however. So if you take a look at the domain, this is a radical, which means there are things that I cannot have underneath the square root function. Negatives. So everything that's underneath here right now, 2x minus 1, it has to be greater than or equal to 0. Make sense? And we can solve that just like we would solve an equation if it were equal to 0. I add a 1 and I divide by 2. So the x values actually have to be greater than 1/2. So in terms of my domain goes from 1/2 and up to infinity. Range is actually fairly easy to think about as well. Think about the kinds of values that come out of a square root function. Every time you take a square root of something, what kind of number do you get? What's the square root of 5? I don't want to do 5. 4. What's the square root of 4? 2. What's the square root of 64?
No, it's even.
8. Not always. Square root of 9.
Oh, no.
3, so not even.
Positive.
Positive.
Yeah.
It's positive. I never take square roots and get negatives, right? Now we could get 0. The square root of 0 is 0, but I never get anything negative. So my range is also quickly determined to be 0 to infinity. I can't get negative values out of a square root function. Okay, they're not defined. So that's cool. Intercepts. Well, my intercept are determined when x and y equals 0, right? So intercepts. So x-intercept is when y equals 0. And my y-intercept is when x equals 0, which is the easier of the two. So let's do the y-intercept first. If I let x equal to 0, what do I get? I get -1 underneath a radical, which doesn't exist. So there is no y-intercept, right? Because when I try to let x equal 0, I get an imaginary number is what I really get. And imaginary numbers are not on our real number plane. Okay, so we've actually already done the x-intercept. We did it by sort of accident up here when we said that this would be greater than or equal to 0. If I just change all those to say equal to 0, I will also get the 1/2, right? Yeah, so my x-intercept is actually at 1/2, 0. So, again, coming to a xy plane, my x-intercept is at 1/2, 0. That's roughly here. I know it won't go beneath the axis, and I know it won't go to the left of my dot. So everything in this graph is going to reside in quadrant 1. Everybody good with that? Okay, so we're going to take a derivative and a second derivative, and we're going to do them really quickly. So if you need to come back and look at these later, please do. But my derivative, this is y, no, it's f of x. F prime of x is equal to 0, or is equal to 1/2 times 2x minus 1 to the -1/2 times 2. Beautifully, the 1/2 and the 2 cancel. This gives me 1 over the square root of 2x minus 1. Everybody good with that? This is never equal to 0, because the numerator can't be 0, it's 1, right? It does equal does not exist. It equals does not exist at the 1/2, right, the one we already found. So in terms of a number line, whoops, that's not straight. In terms of a number line, really, we have the 1/2 on there, but we don't have anything over here to test because there are no domain values over here. All we have to test is something bigger. So if I test the value 1, exactly, what do I get? Positive or negative? I get a positive. So the graph's increasing. But like we knew that, it had to be in quadrant 1, right? So of course the graph's increasing. And if I were to take the second derivative, very similar things are going to happen in terms of the derivative itself. I will get a -1/2, and then I have 2x minus 1 to the -3/2 times the 2 again. The 2's cancel. But I have a negative in front. I end up with 1 over, it's a -1 over, and then the square root of 2x minus 1, and then it's quantity cubed. Again, this will never equal 0. That's okay, but it still does have the does not exist at 1/2, so the sign chart's the exact same sign chart I already did. But now when I do this sign chart, I'm talking about concavity, right? So this sign chart with concavity, here's the 1/2, and I don't have anything to the left. And if I test a value, again, I test the value of 1, and this time it ends up being negative. So it's supposed to be increasing, and it's supposed to be concave down, which you would write those out if you were asked specifically, and the graph looks like that. That's increasing and concave down. And then you're done. No maxes, no mins, no inflection points, because none of that ever changed. Yeah. All right, so homework. Web assigned from 3.5 and 3.6, and there's a quiz next time. That's what's assigned for now. And then the quiz is not on 3-6. It's 3-3, 3-4, 3-5.